Look at any modern computer and it seems to be doing a dozen things at once, but it isn't. Welcome to episode 11 of IT 3000. Today we're pulling back the curtain on the context switch, the quiet, costly trick your operating system performs thousands of times a second to sell you the illusion of multitasking. So let's define the trick precisely. A context switch is the act of saving the complete execution state of one process or thread, every register, every pointer, everything the CPU was thinking, and restoring another's in its place. Because here's the truth underneath. A single core can only ever run one thing. A context switch is simply how it forgets one and remembers another, fast enough that you never notice. So what exactly does the CPU need to remember? Four things, really. The registers, including the program counter, which points to the very next instruction to execute. The stack pointer, so local variables and call frames stay intact. The memory mappings, page tables and MMU state, though only when switching between processes since threads inside one process already share them. And finally, the kernel's own bookkeeping, scheduling data, CPU time accounting, signal masks, the quiet paperwork that keeps the illusion fair. Now, saving all that paperwork isn't free, but it's also not where the real cost lives. The register save and the scheduler's decision take hundreds of nanoseconds, unavoidable but bounded. The expensive part comes after. The TLB gets flushed, so address translations have to be rebuilt. The cache no longer holds the new task's data. Even the branch predictor has to relearn the code path. The switch itself takes microseconds, but recovering from it can take milliseconds. You're not paying for the trick, you're paying for the machine's amnesia afterward. Here's what that amnesia looks like in production. 8 cores, 8 workers, everything humming, cache is warm. Load climbs and someone reasons that more workers means more throughput, so the pool jumps to 800. Suddenly the scheduler is thrashing. Thousands of switches per second per core, and every switch throws away the cache and TLB the previous thread just warmed up. CPU sits pinned at 100%, but throughput collapses. The machine is busy, just not with your work. Before we go further, 3 terms worth untangling, because they get mixed up constantly. A context switch is what we've been discussing. A different task takes the CPU, full state saved and restored, and it's expensive. A mode switch is the same task briefly crossing into the kernel for a system call and back. No task change, far cheaper. And preemption isn't a switch at all. It's the cause. The kernel taking the CPU by force rather than the task politely handing it over. With those distinctions in place, it's worth zooming out. Each concept we've touched on here, the scheduler that decides who runs next, the time slice that bounds how long they get, the CPU cache and TLB that quietly pay the price, the thread pool that amortizes it, and the latency you feel when it all adds up. Each of these is its own episode ahead. We start next with the scheduler, the mind behind the sleight of hand. So here's what to carry with you. The context is everything a CPU needs to resume: registers, stack pointer, memory mappings, kernel state. Thread switches are cheaper than process switches because the memory map stays put, and the real cost isn't the switch itself, it's the cold cache that follows, which is why piling on more threads rarely buys you more throughput. That's the price of appearing to do many things at once. See you in the next episode.